Have you ever wondered how the 3-pound organ in your skull relates to the artificial intelligence systems that can recognize your face, translate languages, or even generate art? Today, we're going on a journey from the biological neuron in your brain to the artificial neurons powering modern AI. By the end of this video, you'll understand exactly how both work and why AI researchers borrowed from biology to create one of the most powerful technologies of our time. Let's start with the real thing, the biological neuron. Your brain contains approximately 86 billion of these remarkable cells, and they're responsible for everything you think, feel, and do. A biological neuron has three main parts. First, the dendrites. These are like branches of a tree, receiving signals from other neurons. Second, the cell body or soma, where all the processing happens. And third, the axon, a long cable that transmits signals to other neurons. Here's how it works. When other neurons send signals, neurotransmitters, chemical messengers, cross tiny gaps called synapses and bind to receptors on the dendrites. This causes electrical changes in the receiving neuron. The neuron is constantly summing up all these incoming signals. Some signals are excitatory. They push the neuron toward firing. Others are inhibitory. They push it away from firing. The neuron integrates all of these inputs in its cell body. And here's the critical moment. If the combined signal reaches a certain threshold, typically around -55 millivolts, the neuron fires. It generates an action potential, an electrical spike that travels down the axon at speeds up to 120 meters per second. This is an all-or-nothing event. The neuron either fires or it doesn't. There's no halfway. When the action potential reaches the end of the axon, it triggers the release of neurotransmitters into the synapse, passing the signal to the next neuron in the chain. And this process repeats billions of times per second across your brain. But here's what makes the brain truly powerful. It's not about individual neurons, it's about networks. Neurons connect to thousands of other neurons, forming intricate circuits. These networks can learn and adapt by strengthening or weakening their connections, a process called synaptic plasticity. This is the biological basis of learning and memory. Now let's jump to 1943. Two researchers, Warren McCulloch and Pitts, asked a fascinating question. Can we create a mathematical model that captures the essence of how a biological neuron works? Their answer became the artificial neuron, the building block of modern AI. An artificial neuron is beautifully simple. Instead of dendrites, it has inputs, just numbers. Let's say x1, x2, and x3. These could represent anything: pixels in an image, words in a sentence, or features of a dataset. But not all inputs are equally important. Each input has a weight, W1, W2, W3. These weights are like the strength of synaptic connections in the brain. A large positive weight means that input is very important and excitatory. A negative weight means it's inhibitory. The artificial neuron performs a weighted sum. It multiplies each input by its weight, adds them all together, and adds a bias term B. This bias is like the neuron's baseline tendency to fire or not fire. Now comes the activation function. This is where the artificial neuron mimics the biological neuron's threshold behavior. In the original model, they used a simple step function. If the sum is above a threshold, output 1. If below, output 0. Fire or don't fire. Modern neural networks use more sophisticated activation functions. The sigmoid function creates a smooth curve between 0 and 1. The ReLU, rectified linear unit, outputs 0 for negative inputs, and the input itself for positive values. The tangent hyperbolic function ranges from -1 to +1. Each has its advantages for different tasks. Let's compare. A biological neuron receives chemical signals through dendrites and sums them in the cell body. The artificial neuron receives numerical inputs and computes a weighted sum. A biological neuron fires if it reaches a threshold. The artificial neuron applies an activation function. A biological neuron transmits signals through axons. The artificial neuron passes its output to the next layer. The artificial neuron is a dramatic simplification, but it captures the core computational principle. Integrate multiple inputs, apply a threshold, and produce an output. Just like in the brain, the real power emerges when we connect artificial neurons into networks. Let's build one from scratch. We start with an input layer. Let's say we're trying to identify handwritten digits. Each input neuron receives 1 pixel value from the image. For a 28 by 28 pixel image, that's 784 input neurons. Next, we add hidden layers. These are layers of neurons between the input and output. Each neuron in the hidden layer connects to every neuron in the previous layer. This is called a fully connected or dense layer. The first hidden layer might have 128 neurons, each performing its own weighted sum and activation function. Here's where it gets interesting. Each connection has its own weight. With 784 inputs and 128 neurons in the first hidden layer, that's over 100,000 connections, each with a weight that needs to be learned. We can add more hidden layers. Deep learning gets its name from these deep networks with many layers. Each layer learns to detect increasingly abstract features. In image recognition, the first layer might detect edges, the second layer might combine edges into shapes, and deeper layers might recognize complex objects. Finally, we have the output layer. For digit recognition, we'd have 10 neurons, one for each digit from 0 to 9. Each neuron outputs a probability, how confident the network is that the input image represents that digit. Let's watch data flow through the network. We feed in an image of a handwritten 7. Each pixel value enters the input layer. The first hidden layer performs 128 weighted sums and activation functions. These outputs become inputs to the next layer. Layer by layer, the information transforms until we get 10 probability scores at the output. The neuron corresponding to 7 lights up with the highest value. The network has made its prediction. But here's the critical question. How did the network learn which weights to use? This is where the magic happens. We start with training data, thousands or millions of examples where we know the correct answer. For each example, we feed it through the network and compare the prediction to the actual answer. A loss function measures how wrong the prediction is. If the network predicts 3 but the answer is 7, the loss is high. If it correctly predicts 7, the loss is low. Now comes backpropagation and gradient descent, the learning algorithm. Imagine the loss function as a hilly landscape, and we're trying to find the lowest valley. We calculate the gradient, the direction of steepest descent, and adjust all the weights slightly in that direction. We repeat this process thousands or millions of times. Forward pass through the network, calculate the loss, backward pass to adjust weights. Gradually, the network gets better and better at making correct predictions. The weights evolve to capture meaningful patterns in the data. So how similar are artificial and biological neural networks really? Let's break it down. The similarities are striking. Both systems use networks of simple processing units that integrate multiple inputs. Both use some form of threshold or nonlinearity to produce outputs. Both systems learn by adjusting connection strengths, and both can perform remarkably complex computations through the interaction of many simple units. But the differences are equally important. Biological neurons communicate with electrochemical signals. Artificial neurons use numbers. Biological neurons have thousands of connection types and neurotransmitters. Artificial neurons typically have one type of connection. Biological brains are massively parallel, with billions of neurons operating simultaneously. Artificial neural networks typically process one example at a time, though modern hardware is closing this gap. Energy efficiency is dramatically different. Your brain runs on about 20 watts, less than a dim light bulb. A large artificial neural network can require megawatts of power during training, enough to power thousands of homes. Speed is inverted. Biological neurons fire at most 1,000 times per second. Computer processors operate at billions of cycles per second. Yet your brain can recognize a face instantly, while computers need millions of examples to learn the same task. Biology makes up for slow components with massive parallelism. Learning is very different. Artificial neural networks typically require huge amounts of labeled data and thousands of training iterations. You can learn to recognize a new object from a single example. Biological brains learn continuously throughout life without catastrophic forgetting. Artificial networks often forget old tasks when learning new ones, and the brain is far more complex. It has multiple types of neurons, sophisticated temporal dynamics, neurotransmitter systems, astrocytes, and other support cells, and architectural principles we're only beginning to understand. Artificial neural networks, despite their impressive capabilities, are crude approximations of biological intelligence. So where does this leave us? Artificial neural networks began as simplified models of biological neurons. Over decades, they've evolved into powerful tools that can translate languages, generate images, play complex games, and assist in scientific discovery. But they're not brains. They're inspired by brains, but they've become their own computational paradigm with unique strengths and limitations. Understanding both systems, the biological and the artificial, gives us insight into intelligence itself. The story of neurons, both real and artificial, is ultimately about the power of networks. Whether made of cells or silicon, magic emerges when simple units connect in the right ways. As we continue to study the brain and develop AI, we're learning that the question isn't whether artificial intelligence will work exactly like biological intelligence. It's what we can achieve by understanding the principles they share. Remember, biological neurons use electrochemical signals and integrate inputs to fire action potentials. Artificial neurons use weighted sums and activation functions. Both become powerful in networks, and both systems learn by adjusting connection strengths. This is the foundation of both natural and artificial intelligence. Thank you for watching. Understanding these fundamentals will serve you well as you explore the frontiers of neuroscience and artificial intelligence.